I'd like to begin this course on basic physics with a few very general remarks on various aspects of this course about physics itself in general, what the nature of the subject is like, what it is we are going to focus on, and so on. And just to remind myself and to make sure I don't forget anything, I have written down here a set of topics, if you like, or points, and these are the points we will discuss today in today's lecture and continue with these points as we go along. The first thing is about the edifice of physics. What I mean by this is that over the last 400 years or so, it has turned out that we have built up, with the help of experiment, observation, analysis, our instruments, our various probes into nature, the mathematics, and so on, we have built up a sort of picture or a building, if you like, which we call physics. This the aim or objective of this picture is nothing less than the understanding of the universe itself, the physical universe, and the laws of nature as they reveal themselves in the workings of the physical universe. So this is what I mean by the edifice of physics. But the very first thing that we have to understand immediately is that this building is a huge building. We have discovered that it really has many more floors than we are daily used to in our daily experience, and that is made precise by understanding what's meant by the ranges of physical quantities. So let me take a few minutes to tell you how vast the scope of nature is and how small our own facility with a small portion of this range is. And in order to make this discussion accessible to you, let's speak in terms of quantities with which you are familiar, namely mass, length, and time. I believe that we understand at a fairly early stage in the study of science or physics that mass, length, and time are primary or basic quantities in some sense. So let's look at these quantities, and here is mass, here is length, and here is time, and let's use the symbols m, L, and T for these quantities. And now I ask the question, what's the smallest mass that we can think of or we've understood or come to terms with, and what's the largest mass that we've encountered so far? And you'll immediately realize that to write specific numbers down, I need a choice of units. And the first thing we have to agree upon is that in modern science today, it's been accepted that we use what are called SI units or standard international units. So all my numbers are going to be in SI units. In these units, mass is measured in kilograms, denoted with kg, the symbol. Length is measured in meters, for which the small m symbol is used, and time is measured in seconds, for which the symbol s is used. You're familiar with this, so I'm going to stick to these units. In kilograms, for length, sorry, this is meters here, so not mass. So it's kilograms, meters, and seconds, and in these units the smallest mass that we've encountered is perhaps the mass of the electron, and this is of the order of 10 to the minus 30 kilograms. So in kilograms it runs from minus 30 upwards through the masses of protons, neutrons, nuclei, atoms, molecules, people, stars, galaxies, and so on, right up to the other end, which is the estimated mass of the universe itself. Now this, of course, we don't know how big the universe is, so we don't know precisely what its mass is, but we have a reasonable estimate of it. We can estimate what the number of stars in the sky is, what's the number of galaxies, what's the number of stars in each galaxy on the average, and from adding all that together and then adding up the mass, estimated mass of the hydrogen clouds in between galaxies, in between stars, and then multiplying the whole thing by another factor of nearly 100, because we believe there exists a thing called dark matter and dark energy. Finally, we have an estimate which is at least of the order of 10 to the 55 kilograms. So that's a huge 85 order of magnitude range in masses that physical science has exposed. Okay. Then in length, the smallest length we can encounter is probed at the highest energy accelerators, and this length is of the order of 10 to the minus 18 or so, give or take an order of magnitude, about 10 to the minus 18 meters. And actually it will turn out that we can think of a, and I am going to come to this very shortly, we can think of a much smaller length scale, and that is of the order of 10 to the minus 35 meters, and I will come back to it. I put it in parentheses here for a specific reason, because it is not the length of a specific object, but rather a fundamental length itself, and we will see what I mean by that. At the other end, the longest length we can think of is the radius of the known universe, and this is of the order of 10 to the 26 meters. So once again you see that there are 44 orders of magnitude here. In time, the smallest times we can probe directly have to do with what are called nuclear forces, strong interactions, and these have characteristic time scales of the order of 10 to the minus 23 seconds. So I emphasize again, we have instruments, we have probes by which we can actually compute or actually measure indirectly lengths, time scales of the order of 10 to the minus 23 seconds. Okay. At the upper end, the longest time scale we can think of is of course the age of the universe itself, and today it is believed the universe is 13.8 billion years old. So in orders of magnitude it is of the order of 10 to the 17 seconds. So once again you have 40 orders of magnitude here in time, more than 40 orders of magnitude in length, and nearly 80 orders of magnitude or whatever in masses. It is a huge canvas. These are orders of magnitude, these are not just factors but orders of magnitude. Okay. So nature's canvas is a very vast one, and what we are used to in our daily lives is a much smaller range here. So it is not surprising that we have to sometimes modify the laws of physics or use better laws of physics when we want to understand what is happening in the very small or on the very large, as opposed to what is happening in daily life. For instance, if I want to know what the length scales and mass scales and time scales are for the motion of this piece of chalk, I would use Newtonian mechanics. On the other hand, if I want to know what to do with electrons, individual electrons or individual galaxies for that matter, I would have to use more sophisticated kinds of laws of motion. Okay. So the ranges of physical quantities is vast. Of course, once I say masses, lengths and time scales are of this, have this large range, it stands to reason, it is obvious that derived quantities such as velocity or acceleration or force or energy will also have similarly very large ranges of physical variation. So having said that about the ranges, and we will come back to this theme over and over again, I want to say something about the nature of physical laws. Now this is a very important conceptual part of understanding what is meant by physics itself. Although it might appear trivial to start with, the statement that I would like to make right away is that the laws of physics have a very peculiar nature. They are not like the legal laws that you have in law, for instance, nor are they like the laws which would dictate the laws of mathematics. What I mean by that is that the physical laws here are not absolute laws. So that is a very important point, not absolute. On the other hand, the laws of mathematics are absolute in the sense that once you define the axioms of mathematics, then the theorems that you prove in mathematics within those axioms are absolute truths. Given those axioms, these truths are eternal, absolutely. On the other hand, any physical law that you can think of is a law which has got qualifying clauses, which is valid only in some regions or regimes of physical parameters. Only for certain ranges of variation of physical quantities are these laws valid. To give you an example, if I were to ask the simplest of laws that you might think of, Newton's law of motion, which says the force is the mass times acceleration, this has many qualifying clauses. It is not true as an absolute law for all kinds of objects or for all kinds of accelerations or forces. It is only true in the regime of what is called Newtonian mechanics. namely the object should not be traveling fast as compared to the speed of light. They should not have speeds which are fractions, good fractions of the speed of light in vacuum. They should be moving much slower than that. They should not be extremely small. You cannot apply Newton's law to a single electron except under very special circumstances and approximations. Certainly the laws of Newton, the original Newtonian mechanical laws, are no longer valid when you come to an object as small as that, as an electron, or an object which moves as fast as an electron can under suitable circumstances. So in that sense, physical laws are not absolute. They apply in certain regimes or ranges of physical parameters, not the entire range in general that obtains in nature, but a much smaller range. And this is one of the very important tasks of physics, is to find out what are the ranges of applicability of various physical laws. For instance, if you say Boyle's law in the theory of ideal gases tells you that the product of the pressure times the volume of an ideal gas is a constant for a given mass of gas at constant temperature. On the other hand, this law is not true for all gases. It is certainly not true if the interaction between the molecules in a gas becomes significant, then the law breaks down and you have to replace it with a modified form of Boyle's law, a more sophisticated form of law. So in this sense, physical laws are not absolute. This is a very important point. It looks very trivial, but it is crucial to bear that in mind, because then you begin to understand what the nature of these laws is, and you begin to understand why it is that these laws have to be constantly refined in some sense. Okay. So we have talked about the range of validity of these laws. The next point I want to make is that there is a quest in physics, there is an effort being made, and that has been there true right from the beginning of the subject itself, to unify these laws and to reduce the number of independent laws. Again, I think an example will immediately tell you what I am driving at. If you took the theory of ideal gases, which you learn in the context of thermodynamics perhaps, there is something called Boyle's law, there is something called Charles's law, there is something called Henry's law, and so on. There is a variety of laws in this case, but the fact is these are all based on a single law, and that single law is the so-called equation of state of an ideal gas. The statement that the pressure times the volume of an ideal gas is equal to the number of moles times the gas constant times the absolute temperature. This ideal gas law has within it, contains within it, all these independent laws that I talked about, such as Charles's law or Boyle's law and so on. For instance, if you kept the number of moles of the gas constant and the temperature constant, then since R is a constant, PV is a constant. That is Boyle's law. So there is this quest to unify and to reduce the number of independent laws, and that is a primary driving force in research in physics, to try to unify these laws. You would have heard about this quest for unifying the fundamental forces of nature. That is part of this program. In fact, it is the most sophisticated part of this program, is to try and see if all the interactions in the universe that we know of can all be brought into one unified picture. Not yet succeeded, but this is the quest. So having talked about the nature of physical laws, we will say more about this as we come along. Let us go on to a very crucial topic which I am going to spend a lot of time on, namely physical dimensions. Okay. With every physical quantity we attach a physical dimension, and this dimension is based on the primary dimensions, physical quantities, dimensionalities, namely mass, length and time. In other words, every physical quantity has some physical dimensions. There are physical quantities which are dimensionless. To give you an example which we are going to use very shortly, a quantity like area, the physical dimensions of it, and I am going to put a square bracket here to denote the physical dimensions of a particular quantity. This here is the square of a length, and I will write this as L squared. And of course we measure area in square meters in standard international units. So in that sense, there are quantities which have physical dimensions which are powers of combinations of m, l and t in general. Velocity, for example, or speed equal to LT inverse, which stands for L divided by T. So, it is measured in meters per second, as you know, and so on. So, physical quantities have dimensions which, if they are dimensional, which are combinations of m, l and t, certain powers of m, l and t, including negative powers and possibly even fractional powers. We will see what that means. Okay. On the other hand, there are lots of physical quantities, measurable quantities, which are dimensionless. For instance, pure numbers like 2 or 3 or 4 and so on, without any units attached to them, they are dimensionless quantities. Here is another dimensionless quantity, angle. So, if I want to know the angle between two straight lines, what I do is to draw an arc of a circle and then take this arc, and this is the radius, and this angle is arc divided by radius. Since this has dimensions of length and this has dimensions of length, these two cancel each other out and angle is dimensionless. Okay. Whether you measure it in degrees or in radians is a separate matter of detail. In physics we always, in science we generally measure angles in radians always. So, I will assume that that is always the case unless I state explicitly to the contrary. Okay. So, here is a physical quantity which is dimensionless. Okay. If you like, it is m to the 0, l to the 0 and t to the 0. So, it is completely dimensionless here. What is crucial is that these physical dimensions help you to check the consistency of equations. But what I mean by consistency is that dimensional consistency is that the left hand side of an equation must have the same physical dimensions as the right hand side always and be measured in the same units. For instance, if you took a law like the force is equal to the mass times acceleration here, then for this law to be consistent, the physical dimensions of force must be equal to the physical dimensions of a mass times an acceleration. So, since this is m and this is Lt to the minus 2, that is the physical dimension of a force. And what is important for you to remember is that once you say a force has a physical dimension of mass times acceleration, namely mLt to the minus 2, then independent of what force we are talking about, this statement remains true. So, notice that I do not say whether this is a mechanical force or a gravitational force or an electric force or a magnetic force or chemical force, I do not care. Every force has necessarily got to have the dimensions of mass times length times t to the minus 2. Now, you might find it convenient to call the units in which you measure it by a shorthand, by some name or the other. For instance, normally I would say, given this equation, I would say force is measured in meters, in kilograms times meters divided by seconds squared, but there is a convenient name for it. So, instead of carrying around m kilogram meter per second squared, I call this, one of these is 1 Newton. So, I introduce a new unit called the Newton, the unit of force, which simply stands for 1 Newton is just 1 kilogram meter per second divided by second squared. That is it. So, that is a matter of convenience. I may or may not want to do this in all cases, but whatever it is, the important point is that the force has a unique decomposition in terms of these primary dimensional quantities, mass, length and time. Okay. Similarly, every physical quantity can be written in terms of a few primary quantities conventionally taken to be mass, length and time. Now, you could ask, oh, while I am at it, I should also say, is that it? Is that all, or do you need more? Is 3 enough in all cases? Well, it turns out that this is an interesting question, that a convenient way of handling this problem is to add quantities to these primary quantities, these 3, as the need arises. For instance, this was okay as far as mechanics is concerned, but the moment you talk about electricity and the transport of charge and electric currents and so on, it turns out it is convenient to introduce a new physical quantity, namely the electric current. Okay. So we need to associate some kind of physical dimension, and what is conventionally done is to say I am going to define an electric current, a unit of electric current called the ampere, and say that that goes along with kilogram, meter, second, and an ampere here. Now I will come to why you need this and what the reason for this extra addition is. Okay. Similarly, when you want to look at quantities which involve, when you want to look at problems which involve the exchange of energy, thermal energy or heat from one object to another, you also need another concept, and that is the concept of temperature. And that is measured in kelvins. The absolute temperature measured in degrees Kelvin, and this introduces for you one more quantity. Similarly, there are a couple more that are introduced, but this is not a very fundamental thing in the following sense. The reason you need one more unit here is because electricity is carried by, current is carried by charges, elementary charges, specifically the charge of an electron. That is a fundamental unit. This charge of an electron, the fundamental quantity here, needs an extra unit because it does not come under m, l and t. It is not a mechanical object at all. Okay. On the other hand, it is possible to choose a system of units such that I stick to these three, m, l and t, but the price you pay for it is that when I talk about electric fields or quantities involved associated with electric or magnetic fields and so on, then the powers of m, l and t that I have for those physical quantities would turn out to be fractional powers. So if you are prepared to accept fractional powers, you can simplify the number of physical quantities or primary quantities, but otherwise you have, it is convenient to introduce one more. Similarly, temperature. Now temperature has an interesting history, and we will say more about this. Turns out that temperature need not have been introduced at all. Okay. It is just another statement, another way of saying energy, which is a basic physical quantity. But temperature got introduced before we understood clearly that heat is just a form of random molecular energy. The random motion of molecules, the kinetic energy associated with the random motion of molecules is what manifests itself as heat. Before we understood this, we thought it was necessary to introduce an extra quantity called the temperature. But you see, that is not an independent quantity at all. But having introduced it, we need something to convert temperature into energy, or to go from energy into temperature, and that involves a fundamental quantity, a fundamental constant called Boltzmann's constant. I will say more about this in a minute when I talk about fundamental constants. And because of the existence of this Boltzmann's constant, we still retain temperature as an independent quantity instead of just saying energy or average energy, and we introduce one more of these fundamental quantities, namely the degree Kelvin, when we want to write down the physical dimensions of quantities. Okay. But these are matters of detail which we will talk about a little later. Coming here back to this, the moment we have m, l and t, and these are the primary quantities in which we are going to express all our physical quantities, we need to also find out whether there are any quantities which appear over and over again in physics and which are constants of nature, if you like. And I should say a few words now at this stage about constants of nature, and we will come back to this over again, because this is a non-trivial concept here, and we need to understand very clearly what I mean by a constant of nature or fundamental constants. So here is a list of fundamental constants which you are already familiar with, but you will immediately see that they fall into several categories. Okay. So called fundamental constants or constants of nature. If I were to ask you to list all the possible constants of nature that you have come across, your first choice, your first guess would of course be something like the speed of light in vacuum. Conventionally denoted by c, and that is a primary fundamental constant of nature. So it turns out. Okay. What is the value of this c? That is well known to you. It is worth remembering the value of some of these fundamental constants because they are very, very basic primary quantities. This is of the order of 3 times 10 to the power 8 meters second inverse. Now of course the speed of light, there are several ways of writing this number here. This has to do with the so called standard international units I talked about, but for our purposes at the moment we will take it to be 3 times 10 to the power 8 meters per second. The other fundamental constant, absolutely fundamental constant, turns out to be Planck's constant. Sometimes called Planck's quantum mechanical constant or quantum constant. This constant here is denoted by the symbol h, which has a value of the order of 6.6 times 10 to the power, is all approximate, into 10 to the minus 34 joule second. Now joule is the unit of energy, and you have to tell me what the physical dimensions of energy are. So let us write that down just to see that we are all clear about what we mean. Energy has the physical dimensions of force multiplied by distance, because the work done by a force in transporting an object a certain distance is found by the product of these two quantities. So this energy has the physical dimensions of force times length. And of course it has got the same physical dimensions of course as work, for instance. Work is a form of energy, and this is equal to m L t to the minus 2 times L, which is m L squared t to the minus 2. Again I emphasize, all possible energy has the physical dimensions of m L squared t to the minus 2. And in standard international units, when I measure mass in kilograms, L in meters and T in seconds, 1 mL T to L squared T to the minus 2, the unit is the joule. It is called the joule and denoted by the symbol J, and that is what has appeared here, out here. Okay. Now in terms of force, the joule is equal to Newton multiplied by meter. So you can write it in several ways if you like. I could have written this J as N times M to stand for Newton multiplied by meter, but this is the standard symbol for it, J. Okay. So this is called Planck's constant. It turns out actually that more useful than this is something called h cross, and that is h divided by 2 pi. So you have to divide this by 2 pi, and it is 1.3 something times 10 to the minus 34, and that is called h cross, and that is the quantity that appears most often in physical applications. Okay. But this is just a matter of definition, just dividing by absolute number here, 2 pi. Remember that 2 pi does not have any dimensions at all. Okay. So what are the physical dimensions of Planck's constant? It is joule multiplied by seconds in terms of units. Therefore the physical dimensions are given by energy, which is joule, multiplied by time, which is seconds. So let us write down right away that the physical dimensions of h cross are m L squared t to the minus 1, because this has to be multiplied by time to give that quantity there. What is the physical dimension? What are the physical dimensions of c? This of course is immediately obvious. This is c equal to L t inverse. It is a speed, and therefore it is distance divided by time. Okay. The third fundamental constant that we have recognized is something that is familiar to you. This is Newton's gravitational constant. So capital G. Its value happens to be of the order of 6.7 times 10 to the minus 11 in standard international units, and these units have to be discovered by us as yet we have to write this down. So let me for the moment write in SI units, and we will write this out in a second. Okay. To find what the physical dimensions of this G are, we need an equation in which it appears, and of course it appears in Newton's inverse square law of gravitation. So the inverse square law of gravitation tells us that the gravitational force between two objects is the product of the masses multiplied by G divided by the square of the distance between them. So this tells us immediately by dimensional consistency that the physical dimensions of force, which is mL t to the minus 2, must be equal to the physical dimensions of G multiplied by the physical dimensions of m1 m2, which is m squared, divided by L squared, because R has physical dimensions of L. Okay. So that tells us that the physical dimensions of G must be equal to m inverse, because I take this to the right hand side, L cubed t to the minus 2. So if you like, I can write this in meter cubed per kilogram second squared. Write it in this form. Okay. But the numerical value in these units is 6.7 times 10 to the minus 11. Now these are three fundamental constants here, and next time we will talk about why these are more fundamental than other constants, and are there other constants that we can think of, and if so, where do they fit into this picture, in what way do they differ from these three fundamental constants. So what you have to bear in mind is that these three at the moment seem to have a very special role, and the next task is to explain why.